We began our discussion of 3D systems in 12.2 with vectors. And as you might know already, a vector is a quantity that has two main attributes. It has a magnitude and a direction. Now, we want to define these vectors in a couple different ways. The simplest way is that a vector goes from one point to another point in a directed fashion. So here, if I have the point A and the point B, I can have a vector that goes from A to B, and I can call this the vector AB with a little arrow, but most often I'm going to want to give it a name. So let's say that this is the vector V, and I know that quantities are vectors when I give them a little arrow above them. That distinguishes them from just scalar numbers. I might have another vector here, for instance, that goes from C to D, and we'll call this vector U. Call this the vector U. U equals CD. And if you imagine that I was a perfect artist and that U and V had the same length and the same pointed in the exact same direction, U looks a little short in this case, but let's imagine that they were exactly the same. In this case, we would just simply write V equals U to show that the two vectors are in fact totally equivalent. We can add vectors. We can combine vectors in a couple different ways. One way is to add them. So let's say I have a new vector V here and its counterpart U here. Well, I can use what's called the head to tail method and combine them this way so that the combined vector V plus U goes like this. V plus U, and this is head to tail. There's an alternative method, and we will use these two methods interchangeably based on what we want, where if I draw approximately the same vector V, fix that up, and approximately the same vector U, I can instead put them tail to tail and kind of project the corners of a parallelogram and now put V plus U right there, and it looks about the same. And this actually gets to one of the most important things about vectors, which is that as long as you preserve their magnitude and direction, as long as you don't change their two attributes, you can move them around. So we can pick up U here and move it back to the tail of V, and our vector sum is still the same. We can pick up vectors and move them all around. So it's not wrong to say that, you know, this is also an image of V and this is also an image of U. You can always pick them up and move them around. You can do other things also. You can multiply them by numbers. So if here I have a vector V, well, here is the vector 2 times V. Or I could have 1/2 times V. I could even have, -2 times V. And in this case, when I'm multiplying it by these numbers, all I'm doing is I'm stretching or shrinking it. I'm not changing the direction. I'm only changing the magnitude. I'm increasing the length or decreasing the length or reversing it, but they're all parallel here. And this, by the way, is why multiplying by these numbers, 2, 1/2, -2, why these numbers are called scalars, because all they do is they scale the vector up and down. Now you might notice that, again, we didn't change the direction of any of these vectors, and this actually gets us to a very important point about vectors, which is that two vectors are parallel. They're parallel if they're scalar multiples of each other. So what that means is that if I have some vector A, and it turns out that A is equal to 2 times B, not only do I know that A is twice as long as B, I immediately know that they are parallel. It turns out sometimes we need a little bit more than just a picture of an arrow. We need to actually put some numbers on things in a coordinate system. One simple way to set this up is to think about vectors that start at the origin. And we'll branch out from there, but it's a good place to start. So here's our little coordinate system. And so let's say we have a vector that starts at the origin and goes off to some point. And we're going to call the point that it touches. So it starts here at the origin and it goes to this point, and we'll call this point A1, A2, A3. This is the vector A. Now in this case, we're going to write the vector A in a slightly unusual way. We're actually going to write the vector A this way. The vector A is actually equal to triangle brace, A1, A2, A3. And you might ask, Mr. Bates, why on earth would we do this? Why do we have parentheses here and triangle braces here? And the answer is because the two are actually very different. That the point A1, A2, A3 is, yeah, it's where the vector is pointing, but the vector A1, A2, A3 is actually a very different entity. So we want to distinguish points from vectors. Now these three numbers, A1, A2, and A3 in here have a very special name. These are called the components of the vector. A1 is the x component, A2 is the y component, A3 is the z component. And again, why do we distinguish them? Because remember, you can pick up vectors and move them around. So to use a 2D example, here's the vector 1, 1. But guess what? This is also the vector 1, 1. This is also the vector 1, 1. This is also the vector 1, 1. As long as they go 1 unit to the right and 1 unit up, they're the vector 1, 1. These are all the vector 1, 1, but they don't all point to the point 1, 1. So we want to make sure to distinguish vectors from points whenever possible. These special kind of vectors that do start at the origin, and not all vectors will, but these special kind that do start at the origin are called position vectors because they tell you the position that they point to, and it's kind of a helpful way to track things through space. So let's say, though, we have one that doesn't start at the origin. Let's say we just have some point out in space here. We'll call this point A. This is the point, we'll call this point x1, x2, x3. And we have some other point here, point B. I'm sorry, x1, x2, x3. What are you doing, Mr. Bates? You can do better than that. What are you doing indeed? A, we'll call this point A, x1, y1, z1. And this is the point x2, y2, z2. If I want a vector, AB, that goes between them, this vector v would be defined by x2 minus x1, y2 minus y1, z2 minus z1. So this is kind of that final minus initial that you might be familiar with from physics for other classes. But again, vectors connote the change from one place to another. If I have that vector, and I would like to know its magnitude, right? If I've got some vector and I would like to know the magnitude of it, well, that's not too hard. I can do the square root of its x component squared plus y component squared plus z component squared. And it's worth noting, if you're doing this in 2D, it's just Pythagoras, it's just x and y for that. What if I want to add up two vectors? What if I've got my good old vectors a plus b, as I had before? How do I do that by components? Well, I know how to do it graphically. By components, it's really not that hard. You just add up the x components, a1 plus b1. That's the new x component. The new y component is, a2 plus b2, and a3 plus b3. A3 plus B3. If I want to multiply it by a scalar, let's say I've got some number C times my vector A, well, I just multiply that scalar into everything. It's C times A1, C times A2, C times A3. And it's important to note this kind of vector algebra does obey all of our normal rules that we've gotten used to in math over the rest of our lives, right? So A plus B is the same as B plus A. you know, and so on and so forth. So they're commutative, they're associative, and distributive. There's one more vector that distributive. There's one more vector that I had neglected to mention before, which is a very special vector. This is the zero vector. It is a vector. It has zero magnitude and points nowhere. But it is important that we do have a zero vector, because if I give you the vector A minus the vector A, I hope you can tell me that that is, in fact, the zero vector. There are three vectors that we're going to talk a lot about this year that are kind of special vectors, and those are the vectors I hat, j hat, and k hat. And it happens that I hat is the vector 1, 0, 0. It has length 1, points in the x direction. J hat is the vector 0, 1, 0. And k hat is the vector 0, 0, 1. I hat, j hat, and k hat. They point in the x, y, and z directions, respectively. And these are a special type of vector. They all have length 1. These are a special type of vector called a unit vector. And a unit vector has a length of 1, has a magnitude of 1. Now it happens that these three vectors are also part of our standard notation in this class, which means that sometimes we will write things in IJK notation instead of component notation. So let's say I have the vector, for a vector A1, A2, A3. Sometimes we will write this vector as A1 I hat plus A2 j hat plus A3 k hat. So for instance, if we have the vector, 1, negative 2, 7, we might write this as I hat minus 2j hat plus 7k hat. It turns out these are examples of unit vectors, but there's lots and lots of different unit vectors we'll see over the year, and you can actually turn any vector you want into a unit vector. So let's say I have some vector A, and I want to turn it into a unit vector. Well, all I have to do is give it a length of 1, so that means shrinking it down or scaling it up until it's got the right length. And so what I can do is I can just take the vector A and divide it by its own magnitude. And we're going to call this a unit vector. We're going to call this A and put a little hat over it. So the hat indicates to us that it is, in fact, a unit vector. So here, again, our j hat and our k hat, the little hats on them indicate that they are unit vectors. So again, we can do this with any old vector we want. So let's take let's just take the vector 1, negative 2, 7. So if I find the magnitude of that vector 1, negative 2, 7, I get 1 plus 4 plus 49, or the square root of 54. This is, in fact, reducible if we want, but we don't need to do that right now. It's actually not important to do that right now. You can do it if you like. And so we could actually write that vector this way. And this is going to bother a lot of your previous math teachers. That's okay with me. 1 over root 54, negative 2 over root 54, 7 over root 54. And I know a lot of your previous math teachers would tell you to never leave a radical on the bottom. And I'm going to tell you in this class that it is okay, because that actually gives us additional information. It lets us know right away what we did. That we found the magnitude of the original vector and we divided by the square root of 54 in order to turn it into a unit vector.